In this section, we're going to use our knowledge of trigonometry and particularly of polar coordinates to work with complex numbers. Now, complex numbers are numbers that have both a real part and an imaginary part. And they arise in many real-world situations, which may seem kind of paradoxical, but they do. But let's start by just looking at a simple equation that we might want to solve. X squared plus 1 equals 0. If I wanted to solve this, I would probably start by subtracting 1 from both sides. But right away here we notice a problem. We're claiming that the square of some number is equal to -1. But we know that that really doesn't make any sense, because when you square a number, it should always be positive, right? Since a negative times a negative is a positive, and of course a positive times a positive is as well. So it doesn't seem like this sentence makes any sense. So one way we can understand imaginary numbers kind of springing into being is to say, well, let's suppose that it is possible to square a number to make -1. If that were possible, then x, using our familiar algebraic techniques, would equal plus or minus the square root of -1, right? So in other words, we're kind of assuming that this square root of -1 makes sense, even though in our experience prior to looking at imaginary numbers, it really doesn't. All right, so this, with the knowledge that the square root of -1, right, is really bogus, because it's saying, what number, when I multiply it by itself, do I get -1? We're going to go ahead and give it a name. And since we don't think it really exists, we'll call it I for imaginary. And so then what we would say is that the solution to this equation is plus or minus I. So, while that all just kind of seems like perhaps we're making stuff up, it turns out that a lot of real-world things require us to use imaginary numbers to describe them. So a couple examples. One would be if we look at alternating current. Okay, so if we look at an alternating current circuit, which are the circuits that run through all our buildings, to describe various components of those circuits, you actually need to use imaginary numbers. Another example is the very building blocks of matter. When we want to describe the position of, say, an electron in an atom, we're going to use a function that has a real part and an imaginary part. So while it seems like we're just kind of playing mathematical games here, it turns out that this idea of an imaginary number has very practical uses. All right. So when I say complex number, what do I mean? Well, a complex number is a number that has a real part and an imaginary part. Right? So we call A the real part and B the imaginary part because it's multiplying by our I. Okay. So just a couple of facts to remember is that I will always mean the square root of -1. And so therefore I squared is going to equal -1, because if you square a square root, they essentially cancel each other out. And so I squared is -1. All right. And then lastly, when we want to talk about two numbers being the same, we say that two numbers are equivalent if and only if both the real and imaginary parts of that number are the same. All right. So one of the things we do with complex numbers is we can put them on a graph that helps us represent them. So since there are always two components to any imaginary number, we need a two-dimensional graphing system to be able to graph them. So contrast this with all the real numbers, right? All the real numbers, it's sufficient just to make a little number line, right? But with complex numbers, since there's a real and an imaginary part, we just kind of turn the horizontal axis into what we call the real axis and the imaginary axis into the vertical axis, and so we can represent any number in this complex number system as a point in the plane. All right, so you may have had some experience with complex numbers in the past, so I just want to do a couple examples that reminds you of how we deal with them. So if I want to add two complex numbers, it basically works exactly as you would expect it to work, which is that we essentially think of this as combining like terms. So my 5 and my 3 are real parts. I will combine them. And then my minus 2i and plus 7i are the imaginary parts. I will combine them. So adding complex numbers works in the exact way you would assume it would. If I want to multiply two complex numbers, then we're going to basically treat the I like it's an x. So if I had 5 plus 8x times 3 plus 2x, I would just FOIL out. And that's exactly what we're going to do with these complex numbers. So first, 5 times 3 is 15. Outside, 5 times 2i is 10i. Inside, 24i. And then last is going to be plus 16i squared. All right, so the interesting thing here is when I multiply these two imaginary parts in the last position, since we know that I squared is -1, it becomes a part of the real part of the number. All right, and of course these two can go together. This is 34i. But -1 times 16 is -16. So I combine those to make -1 as my real part, plus 34i. All right, so we just essentially FOIL out. And then lastly, how do we have to divide when we are working with complex numbers? So if I want to divide 4 plus 5i divided by 1 plus 3i. So keep in mind that we always want to write every number in the complex plane in the form a plus bi. That's kind of this is the acceptable way to write a complex number, or one acceptable way to write a complex number. So I would want to write my result of dividing these like this. And right now it's not like that, because here you see there's no I in the bottom of a fraction. Here I do have an I in the bottom of the fraction. So what you have to do in a case like this is say, okay, what could I do to this fraction so that the I in the denominator will go away? Well, the answer is to multiply by the complex conjugate, which just means write this term again, except for change the sign in front of the imaginary term to a minus. So I multiply by 1 minus 3i. And then I do the same thing on top. So I'm not actually changing the value of the fraction. And so I FOIL out on top. This is 4 plus 5i minus 12i minus 15i squared, all divided by, well, now this becomes 1 plus 3i minus 3i minus 9i squared. And so you can see why it is that I multiplied by this, what we call the complex conjugate, is because those middle terms, which are my imaginary terms, cancel each other out. So what I have now is 4 minus 7i minus 15 times -1, since I squared is -1, all divided by 1 minus 9 times -1. And so -15 times -1 is positive 15, so this becomes 19 for the real part on top, minus 7i divided by 10. And then to really put it in that form, I could change this to 19 over 10 minus 7/10 I. And so there would be my result of dividing these two complex numbers. Now, the last example, when I multiplied in this one, basically one of the points of this section is to show you a different way of approaching these same problems. Okay, so in order to be able to do that, we're going to talk about being able to express complex numbers in what we call polar form. So let's take a complex number and let's put it in the complex plane here. So we have our little point here representing the complex number a plus bi. And let's keep in mind that we just learned how to express points in the xy plane in terms of polar coordinates. Well, this certainly has the same form as a point in rectangular coordinates, the idea that this a is kind of like my x and the imaginary part b is kind of like my y. So I should be able to convert my complex number written this way into kind of a polar form. Okay, so let's just recall that the x value in rectangular coordinates is r cosine theta. So then if we translate to the language of our complex number, the a is like our x value, right? So we just call that a instead. And similarly, we know y is r sine theta, but in this context, the y is the b, the imaginary part. So we can say a is r cosine theta, b is r sine theta. And so this gives us a way of giving the polar form of a complex number. So this here is the real part. This is my a. And then here's the imaginary part. This is my b. And so, of course, the other formulas that govern how we translate in between polar coordinates and rectangular coordinates apply as well. So I've got r squared equals a squared plus b squared, just like before we had r squared is x squared plus y squared. And then the tangent of theta is b over a, just like before we had y over x. And then a couple pieces of vocabulary here. We call r the modulus of z. Okay, so if you've ever heard of the modulus of z, which we denote as it looks like the absolute value of z. That's our r value, which of course would be the square root of the real part squared plus the imaginary part squared. And then finally, theta we refer to as the argument of our complex number z. And then one other note to make is that when we're writing in polar coordinates, there's really infinitely many ways to write any particular complex number, because if you just add multiples of 2 pi to any angle, you just get back to the same place, right? So in this picture here, so this particular theta, if we then go around again so that we have theta plus 2 pi, we're going to end up in the same spot. So, so we have infinitely many ways that we can express our complex number in polar form. Now finally, there's a slick formula called Euler's formula that allows us to write polar form really concisely. And so when I have my complex number in polar form, r cosine theta plus I r sine theta, that can be equivalently written as r e to the I theta. And this is the e that that you have worked with many times. It's just the natural exponent, right? So it's that same number that you're using when you're studying exponential functions. And so this seems kind of strange, and it's unfortunate, but the way to prove that this formula is true actually requires some more advanced calculus. And so if you take kind of a third quarter calculus class, you'll see be able to show why it is that they're equal. But we'll just go ahead and have to take this at face value. So when you use this form, you'll find that arithmetic becomes pretty easy, particularly multiplication, division, also raising our complex numbers to powers, which we'll also study, becomes pretty easy when you do it in this form here. All right, so let's take 3 different complex numbers written in the standard form, a plus bi, and then let's convert them into polar form, and in the end we're going to use Euler's formula to write it. All right, so I know that r squared is going to be a squared, so 1 squared, plus b squared, which is also 1 squared. So r squared is equal to 2. And so r is equal to the square root of 2. Okay, and as we're going here, let's go ahead and sketch this so that we make sure that the answer we come out with in the end actually makes sense. So this is the real part. This is the imaginary part. So if I have 1 plus I, that means I go 1 on the real axis and then up 1 on the imaginary axis. That puts me right there. All right, so r is equal to the square root of 2. And then we know that the tangent of theta is equal to b, which is 1, over a, which is 1. And the time where tangent of theta equals 1, hopefully we're remembering, is at theta is equal to pi over 4, when both the sine and the cosine, or the y and the x value, are both equal to positive 1. So if I was to write it out in polar form, I would say that 1 plus I is equal to r root 2 cosine of theta, which is pi over 4, plus I square root of 2 sine of pi over 4. But then using Euler's formula says 1 plus I is just equal to r square root of 2 e to the I times theta, which is pi over 4. And so for these other 2 examples, I'm just going to write it using Euler's formula because you can see how nice and compact this is. All right, so for part B, we need r squared is equal to negative 2 root 3 squared plus 2 squared. So r squared is 4 times 3 plus 4, which gives me 16. So that means r is equal to 4. And then the tangent of theta is going to equal 2 divided by negative 2 root 3, which is 1 over negative root 3. And then we should recognize those as special values, because I can divide the top and bottom both by 2 and get special values on the unit circle. So I know that this is where my y, or in this case the imaginary part, is positive, as we can see here, and the x is negative, or the real part is negative. And so we're definitely over here somewhere in quadrant 2. And so in quadrant 2, the sine is positive, and the positive 1/2, and the cosine is negative root 3 over 2 when theta is equal to 5 pi over 6. So just writing it using Euler's formula, we get that negative 2 root 3 plus 2i is equal to 4 e to the I times 5 pi over 6. All right, then lastly here, r squared is equal to 5 squared plus negative 5 squared. So r squared is equal to 25 plus 25. R squared equals 50. So r is equal to the square root of 50, but I can simplify that. 25 times 2 inside the square root, and then the 25 jumps out as 5, so it's 5 roots of 2. And then the tangent of theta is equal to negative 5 over 5, which is just negative 1 over 1. And we got to think about, okay, on the unit circle, whenever tangent is 1 or negative 1, that's going to be a special value. So that's going to happen. Oops, let me fix that real quick. That's going to happen when we have square root of 2 over 2 for both cosine and sine, except the top will be negative square root of 2 over 2. And the bottom will be positive root 2 over 2. So when the y is negative and the x is positive, that happens in quadrant 4. So that would mean theta is going to equal 7 pi over 4. So we get that 5 minus 5i is equal to 5 roots of 2 e to the I times 7 pi over 4. So I'm just going to box each of these because on the next page we're going to do some arithmetic with a couple of these, and we're going to come back and use these polar forms that we've got here. So we're asked here to find the product of 1 plus I and negative 2 root 3 plus 2i. So what I want to do is show how slick multiplication works if you have them in polar form. So both of these are ones that we just wrote in polar form on the previous page. So our 1 plus I was this one, and here's our negative 2 root 3 plus 2i here. So instead of 1 plus I, I'm just going to write square root of 2 e to the I times pi over 4. And then here, I'll write 4 e to the I times 5 pi over 6. And the nice thing here, no more foiling required, right? There's no pluses or minuses or anything. So all I got to do is take root 2 times 4, so that's 4 root 2. And then I'm multiplying exponents with like bases. And remember, when we multiply exponents with like bases, you just simply add the exponents. So just using our exponent laws here. All right, now if I'm going to add those in a meaningful way, then of course I'll need a common denominator. So that would be 12. So I'm going to multiply the top and bottom of this one by 3 and the top and bottom of this one by 2. And so I get 4 root 2 e to the I. And since I have an I in both terms, I'm just going to write it like this. 3 pi over 12 plus 10 pi over 12. So this is going to be 4 root 2 e to the I times 13 pi over 12. And this is our answer in polar form. So if that's the way that the answer is requested from us, then it's fine just to leave it like this. Now, if they did want us to put it back into standard form, into that a plus bi form, then what we would do here is we would first write it with sines and cosines. So this would be 4 root 2 cosine of 13 pi over 12 plus I times the sine, I times the square root 4 times the square root of 2 times the sine of 13 pi over 12. And then, 13 pi over 12 is not a special value, so then we would just go ahead and pull out our calculator to get an approximation. And the approximation I get is negative 5.46 plus negative 1.46i. And of course I could put, minus 1.46i, and that's fine as well. So this would be then in standard form. But it is an approximation, of course, since 13 pi over 12 isn't a special value. All right, so one last example here. We're going to find the quotient of 1 plus I and 5 minus 5i. And again, we wrote both of these in polar form in example 5. So let's go back. So that would be these two. So in the numerator here, I have the square root of 2 e to the I times pi over 4. And then in the denominator, 5 root 2 e to the I times 7 pi over 4. So first of all, we can see some nice cancellation happening with those square roots of 2. So that's nice. But then we also know that when we are dividing exponents with like bases, we subtract the exponents. So this can become e to the I times pi over 4 minus I times 7 pi over 4, and then that's all divided by 5 still. That didn't cancel out. And we've already got a common denominator, so that's pretty nice. And so this 5 here, I think I'm going to go ahead and just put it out front so that it is multiplying by our exponent. So then this is e to the I times pi minus 7 pi would of course be negative 6 pi over 4. And then that's going to be negative 3 pi over 2. And so again, this is acceptable if we're just trying to write our answer in polar form. But then if we want to go in standard form, which is kind of nice to do in this one, I think, because negative 3 pi over 2 is a nice value. We would write 1/5 cosine negative 3 pi over 2 plus I times 1/5 sine of negative 3 pi over 2. So thinking about the unit circle for a second here, the cosine of negative 3 pi over 2, so negative 3 pi over 2, I'm going to go in the clockwise direction, 3 pi over 2, so that puts me right here. So what that means is that the cosine is 0, and the sine is 1. So this equals just simply 1/5 I. And so what I think is kind of nice here is let's go ahead and graph in the complex plane these two original complex numbers and then also the result. So if I sketch this out here, here's the real axis, here's the imaginary axis, and then, you know, let's put 5 here, -5, -5, and 5. So then 1 plus I, you know, that's just going to be right there, right? Over 1, up 1. And then 5 minus 5i would put me right here. And so the idea is that I have taken those two numbers in the complex plane, I've divided them, and it's given me the result 1/5 I, right? So there is a 0 for the real part and 1/5 for the imaginary part. So that puts me just right, right there. Okay. I'll have to ignore that. Let me cover up this mistaken dot here. So this value right here, that's my result of dividing those two numbers.